हेलो। मेरे को भूषण ने आए फोटो।
Good morning, sir. Sir, shall we start?
कितने पार्टिसिपेंट्स हैं नितिन जी?
Sir, right now there are 15 participants and some students
मैं
are,
देख रहा हूँ वो हाउ मेनी आर एनरोल्ड.
sir, more than 100 participants are enrolled in this workshop.
ओके ओके. मेजॉरिटी आर टीचर्स आर स्टूडेंट्स?
Majority are the teachers and few faculty, few members are from the industry.
ओके, वेरी गुड. गुड मॉर्निंग परेश जी.
Oh, good morning, sir.
How are you, sir?
हाँ, आई एम गुड. आप देख लीजिए, जब whenever you feel comfortable you can initiate.
Yes.
We can start, sir, because already we are running out of time. It's 11:10, so I think we should start.
Okay.
Okay, so good morning to all the participants and the respected Dr. M.A. Mulla sir. I am Nilesh S. Mahajan, Assistant Professor, Department of Electrical Engineering. Welcomes you to the fourth day of AICT sponsored STTP on digitally controlled power converters for industrial and renewable applications, phase 3 under the AQIS scheme. It's my privilege to introduce the today's speaker, Dr. M.A. Mulla. Dr. M.A. Mulla sir received his bachelor degree in electrical engineering from the Sardar Vallabhbhai National Institute of Technology, Surat, in June 1995. He did his master's in from MS University, Vadodara in 1997 and PhD degree from SVNIT Surat in 2015. He has more than 23 years of teaching experience. He is currently working as an associate professor in the Department of Electrical Engineering at Sardar Vallabhbhai National Institute of Technology, Surat, since 16 September 2010. His research interests are solar and wind energy conversion, AC-DC converters, DC-AC converters, power quality, and active power filters. He has established a laboratory to teach power electronics and renewable energy power quality and electrical drives courses with hands-on based learning. He has total 65 publications at his credit, which include 2 books, 2 book chapters, 27 journal articles, and 34 conference articles. He is a senior member of IEEE, International Association of Engineers, Indian Society of Technical Educations, and Institution of Engineers, India. So I would like to request Dr. M.A. Mulla sir to please start today's session. Over to Mulla sir.
Thank you, Nilesh.
Thank you, sir.
Thank you. I thank organizer to invite me for this event. I am just reading few names. So all of you, can you please switch on your camera? I wish to see to whom I am talking. Lohani ji, Chavan ji. Okay. Syam is Singh. Good morning, Syam.
Good morning, sir.
Prasan. Good morning, Prasan ji. Pawar sir is in.
Good morning.
Good morning. Tanvir, Tanmay, Suhas. Tanvir is in. Ashok, Ghosh, Can you please turn on your camera so that before we take technical content, we can understand what is the gathered crowd? Radhika, Manikandan, same person who was there last course.
Sir. Yes, sir. Yes, sir.
So Manikandan ji. And there is a VS power also and SV power also. So SV power ji. That I can understand.
He's from Dhule. He's from Dhule.
But name is all same SV and VS. So can you please switch on your camera? Last request. Are you there, Radhika? D goes is seen. Ashok Kumar, some do not want to switch on like that. It's okay. Those who are uncomfortable. So this is a difficult period. These all programs are to interact with each other, share each other's experience, and get some direction for whatever activity we are doing, maybe industry or research or teaching. So in difficult time, this virtual mode, it is happening. There are many plus, so many programs are happening. Programs are normally starting on time, getting completed on time. And the negative sides are we are talking to laptops most of the time. So others are even not willing to say yes or no. So we can make it a little bit interactive. We can understand each other, and then we should have your time is also important. So you should interrupt at any point of time and share maybe a better idea or some question you can pose where other can participate, and that way interaction should happen. So I assume that remainings are very shy persons, or maybe they don't want to share their identity or beautiful photographs. So I will begin. So today's talk is around VSC-based fax controller. So it is voltage source converter based fax controller. So whatever problem will come in transmission line because of AC transmission line, it is very difficult to maintain power flow and reactive power. So those problems, how we can address utilizing this technology called as a VSC based fax controller. So as Nilesh ji said, the unique thing what we attempted at Surat is all these courses via some small laboratory experiment, how we can digest all this concept of shunt compensation, series compensation, then instantaneous power theory, DQ transformation. So that we have attempted here. So this lecture also treatment will be little bit practical oriented only. So how to do all these things in the laboratory? Okay. So I have a few video clips also where these things I can demonstrate, and at the same time uh, just to make sure that it will happen. Many time video will not work. So in my PPT I have included results of all these compensators also. So that is how I have planned. So I would like to begin via playing one small clip where I can show you what all I am going to show you. So you can give me the feedback. If it will work, then remaining video clip I will utilize. Otherwise, I will try to talk with my PPT only. So is my Google Chrome screen visible?
Yes, sir.
Okay. So this is the thing what I am going to speak. We'll start with theory and then how to design all this. So let me just explain you. So this is the main supply. This is the main supply, and there is a transmission line. So it is emulated via some pi network. So there are 3 pi networks. So some kilometer each section present. So that way a transmission line is created. Okay. So we can say this is a sending end and this is a receiving end. Okay. Now, in order to see what is happening at sending end and receiving end, 2 multi-parameter meters are connected, both the ends. So we can observe the magnitude of voltage. We can observe the active reactive power at sending end, receiving end. We can observe the power factor. So any entity, multi-parameter meter will represent. Okay. Now to understand the effect of loading, so ultimately electrical network is to supply active energy. So we will have different load bank here. So suppose number of resistances, so that is active loading. Only active power the load will be drawing. So this is a place where we will connect the load. So we'll be having a variable R load, a variable RL load, and variable RC load. So that we will connect here. So some effect at the receiving end voltage and power factor and power will be observed here. So like we know that as we load the transmission line, the voltage will drop. So this voltage will go down and down. And the reverse effect is with capacitor. So whenever there is a capacitive loading, this voltage will be boosted. So this voltage will be higher, even higher than a sending end voltage. Okay. So this is one test setup where a real transmission line can be simulated and the effect of resistive, capacitive, inductive loading on this transmission line can be studied. Okay. Now today's subject is fax devices. So if at the receiving end, if I connect some shunt device, okay, then how we can overcome this problem, how we can change the magnitude of this voltage. Okay, so that we will try to understand. So voltage source converter is 6 IGBTs will be there, 1 DC link capacitor and 3 interfacing reactors. So this will make the shunt compensator. So when this is connected at the receiving end, now the reactive power requirement of the load. So for resistive load it will not work out. So for RL load, we can supply capacitive reactive power from here itself. For RC load, we can supply inductive reactive power from here itself. So that will not come from transmission line. So as a result, this voltage will be boosted. So you will be having good receiving end voltage provided the reactive power requirement. So reactive power is a 90-degree phase shifted voltage and current. So average value of that waveform is 0. So that is how without any source it can be supplied. So capacitor and inductor can exchange energy with each other and infinitely they can keep exchanging the energy. So we don't require any source. Capacitor will give, inductor will store, inductor will give, capacitor will store. So that way reactive energy exchange can happen between lagging current and leading current. So now why this third power meter? So under this scenario when shunt compensation is happening, so what is the voltage of the load? What is the power factor of the load? What is the active reactive power of the load? That will be different than the receiving end. So at receiving end now this shunt compensator is also there and load is also there. So that is why 2 power meters on the receiving end, one to represent load values and another to represent receiving end values. Okay. Then we extend the experiment further. So there is a series compensator. So in case of series compensator, voltage we will have to inject in series. So we require some injection transformer, and once again through power electronics, so voltage source converter, we will generate some voltage and we will inject in series. So via series compensation that can be established, and universal one is one where you have what is termed as UPFC, Unified Power Flow Controller. So you have shunt arrangement also and series arrangement also. So both the arrangements are working together, and that is controlling the active reactive power requirement of the load and making sure that receiving end voltage will have the required values. Okay. So this is the subject what I am going to talk about. Now in order to perform all this experiment, suppose only shunt compensator experiment you want to do. So you don't require series experiment, series compensator. So what we require, so we'll have to bypass this transformer. So one switch we will require where if we short the transformer terminal, it is bypass. Okay. In order to connect shunt compensator, one more switch we will require. In order to connect series compensator, one more switch we will require. So that is why there are 3 MCBs seen here. Okay. So suppose only shunt compensator experiment. So we will bypass this. So this MCB will be on. We have to work with shunt compensator, so this MCB will also be on, but the series MCB will be off. So this converter will not produce any voltage and it will be in off position. Whenever we want to experiment around series compensator, then we will make shunt compensator switch off. So we will not be operating this shunt arrangement, only series arrangement will be operating. And when we require UPFC operation where both shunt and series compensator is required, then this MCB must be off for series. So this will connect the transformer and then both this MCB will be on. So that is how via these 3 MCBs we can create all 3 experiments: shunt compensator, series compensator and shunt series, that is UPFC compensator. Okay. So just to check whether video will work with properly or not, the first video that I will play here, so we will not be doing something with fax controller. I will speak before going to that experiment. So we will just load this transmission line with RL and RC loading, and the effect of that over here will be demonstrated here. So I'll be playing this clip, and I want some feedback where you will say that it went well, and I can include remaining video clip in my talk, or alternatively, as I told, the result of this experiment I have included in presentation. So through presentation also I can explain all the parts. Okay. So can I play the clip, Nilesh?
Yes, sir.
Okay.
Aim, we want to check the effect of different loads. So we have to connect our transmission line to load. So this is a last MCB you have to turn on, which will be connecting your transmission receiving end to your load. So you will turn on MCB E. Okay. So we have different kinds of load. So right now the selection is on the R load. So we will check the effect of R load on our transmission line. So we will first lightly load the transmission line. So we'll turn on only switch 1. So as you can see, big drop in voltage is observed over here. As you will increase the load gradually, the voltage will be dropping. So after turning on all 4 MCB, we are getting some drop over here, and voltage is 113 volt, we can say that. So now if we will change over to RL load on the same quantity of load. So we will connect full load, but that too of RL load. So we just have to change this switch to RL load. As you can see, more 2 to 3 volts are dropping over here. In case of RL load, the voltage is dropping. In case of capacitive load, the voltage will be increased. So in the same condition, in the same quantity of load, we will just change over to RC load using the same switch. So after changing towards RC load, we were originally we have 120 volt transformer, but right now we are getting 134 volt. So the capacitor is overcharging our transmission line. So we are getting boosted voltage at the receiving end. So accordingly you can change the combinations of the load and you can observe the voltage. Now if you want to observe the power factor of the line, we have multi-parameter meter over here. So we will just change to power factor. So over here you can see we are getting 0.6 capacitive power factor. The same thing will be displayed on the load side of the meter. If we change, as you can see, capacitive 0.6. If we change the load to RL load, then we will get lagging power factor. So here you can see 0.6 lagging in both the meter.
So was it okay? Hello,
Yes, sir.
participants.
Sir, is it okay, sir?
Okay, so how many of you appreciate this, that this is really what is happening in AC transmission line? So is it okay? So this is a small demonstration where same thing we can verify in the laboratory as well. Syamji, could you see the clip properly? D. Syam? Radhika, some feedback? Could you see the clip properly? Are you there, Radhika, Syam? So I need to assume that they will not speak.
Hello?
Yes, Radhika ji.
Hello?
Hello.
Hello?
Yes, Radhika ji. Yeah, I can hear.
I didn't watch the video from the
You didn't watch the video. Okay.
beginning.
Sorry?
Hello?
Yes, Radhika ji.
I didn't watch the video from the beginning.
Beginning, but whatever part you watched, was it audio, video, all thing okay?
Yeah,
Okay.
that is fine.
Okay. And this is a small transmission line model where the effect what will happen really in field is established. And then today's subject, VSC-based FACS controller, how we can overcome this problem. That we will try to discuss further. Thank you for the feedback.
Thank you.
I will run my presentation now, and then we will try to take the topic, and then if required we can come down to some video clip once again.
Sir, is there any problem?
We can hear you, sir. Sir, your voice is not audible, sir.
Are you able to see the presentation now? Hello.
Yes, sir.
Are you able to see the presentation now?
Yes, sir. Yes, sir.
Okay. Fine. So sorry. So the title is Design and Development of a VSC-based FACS controller, for which we are gathered here. So the agenda or outline is first we will discuss about what are the power quality disturbances, who is responsible for creating these power quality disturbances, what are the different mitigation techniques we are utilizing for overcoming these power quality problems. So some theoretical part we will try to understand. Then we will introduce this subject. So how this VSC, voltage source converter, is FACS controller are finding their wide application for mitigating power quality problem. That we will try to correlate. Then whatever trainer, some small clip I have tried to demonstrate you. So how we have designed that trainer where real transmission line can be simulated different types of loading effect on the transmission line can be studied, and there this fax controller can be applied for mitigating that. That I will try to share. A major part is control circuit. So some digital controllers, so microcontroller where field information, that is load current, load voltage, we are giving as a feedback, and then automatically that is calculating the reference for voltage source converter and generating require lagging leading current. So that part also I will try to explain. And then test results of this series shunt compensator and discussion. Okay. So I encourage you to interrupt me at any instant of time. Okay. Last, if time will be there, some of you may be working in the same area, so how you can keep interacting with us, what are the possible options, that also I will try to speak about. So can anybody say what is the ideal power system, what we are looking for in AC power system, what is the ultimate desired we want to achieve via this power quality subject? Can anybody comment what is ideal power system we are looking for? When we can say there is no power quality problems?
Voltage must be within specified limit.
Okay, so one quantity is utility should us in one range the value of voltage. Okay. Any other thing?
There is one comment in a chat box from Tanvir Hussain, when no harmonics are present in the system.
So no harmonics are present, we can say current and voltage should remain sinusoidal. That will be the theoretical statement which will take care of harmonics. So current and voltage should remain sinusoidal. Voltage magnitude should be in the range. Any other point? So other point is both voltage and current should be in phase with each other.
Yes, yes.
So if we can make voltage and current in phase with each other, then volt ampere will be equal to wattage. So our transformer capacity is in volt ampere. And in a situation, if all loads are drawing current in phase with voltage and it remains sinusoidal, then we are utilizing minimum possible capacity, VA capacity of supply transformer, and the loading of the cable which is connecting supply transformer to the load, the RMS current we are drawing is least possible. Okay. So these are the few points. So when we can say power quality problem is solved, so voltage and current should be sine and they should be in phase, irrespective of anything. You may be connecting rectifier, motor drive, anything. So all the load should draw a pure sine current and it should be in phase with supply voltage. Then we can say that it is the optimum thing what we can achieve while transmitting power from AC source to the load. Okay. Now who is disturbing this? So one by one, if we take small example like grid is able to give us sine voltage, then the first thing is we will be connecting some motors. So we will start taking some lagging current. We will be connecting some power factor correction capacitors, fixed capacitors. So we will start taking leading currents. So first deviation will come where phase displaced current we will start drawing. Okay. Then this power electronics has penetrated like anything in all the applications. So this is these are the switching circuit which will draw non-sinusoidal current. So another deviation is with a sinusoidal transformer voltage, we will start drawing non-sinusoidal current from this source. Okay. Now this current fundamental component, if we write, it might happen that it is in phase with voltage. But if we try to match volt amperes, that is the RMS current what we are drawing through the conductor, and the wattage, what power the load is getting. Suppose it is a rectifier, so DC side, whatever power load is getting, if you try to match, once again it will not match. So that mismatch is not happening because of phase angle now, but because of non-sine nature of current. So non-sine nature of current is also having same effect what we are having because of the phase displacement between voltage and current. So we are drawing more RMS current from the conductor, more volt ampere capacity of transformer we are utilizing. A transformer which is designed for 50 Hz frequency, other frequency current you are drawing from that transformer. So many issues these circuits are creating. Now story will not be completed here. So it is a bidirectional problem. So on with previous comment, we may feel that only load is creating problem. But it is not like that. Many a time what happens that some load or some units are drawing harmonic current. Then the utility company will ask them that you are drawing harmonic current, so it is disturbing the supply transformer. But the unit will demonstrate that they are not having any power electronics load. They are having only linear load, some motors and resistors and heaters and all that. So still, how come resistor, inductor, capacitor can draw harmonic current? So now the problem will be from the voltage itself. From the voltage itself, some harmonics are coming. So if the utility will not be able to supply pure sinusoidal voltage, one frequency voltage, then small harmonic present in voltage signal, the resistance inductor also will take same that frequency current. So as a result, harmonics will get amplified. Okay. So it is a bidirectional problem. Sometimes it will come from utility. Majority time it will come from load. We say the popularly used term PCC, point of common coupling. So one transformer is supplying several load. So at point of common coupling where different loads are connected, if one of the unit is having a major non-linear current, then the PCC voltage is nothing but your sine voltage plus source impedance drop. So each transformer or generator will be having some small source impedance. So subtracting a non-sinusoidal current drop across that reactor from sine voltage will result into PCC voltage where small harmonics will always be present. Okay. A small experiment like in our laboratory, if we take pure capacitor, our expectation is it should draw leading current and sine current. But you try to see a current waveform of pure capacitor, it will never come sine. So it will never come sine because supply is having a small quantity of harmonic. So capacitive reactance at that harmonic, it is 1 by omega c, will be very small. So its reflection on current will be very high. So pure capacitor, even in our laboratory also, you will not get pure sine current. Okay. So it is a bidirectional problem, and to whom we shall make responsible is very difficult. Sometime it is a consumer, sometime it is a utility, sometime it is a adjacent consumer, not the original consumer, but problem is coming in some other consumer, but it is happening because of the parallel load running from same point of common coupling. So what other sir commented is right. Utility job is to provide one fixed magnitude voltage to all the load, irrespective of how many loads they are connecting to that transformer. That voltage should be of pure sine nature. Okay. And load side, we will have to assure that all the load will draw a pure sine current. So when any load is drawing pure sine current in phase with voltage, we can say the equivalency is like resistance. So utility would like to fill all the loads as resistive load. That is the optimum one where we don't have any power quality issues and pure sine voltage and current and in phase with each other. And all transformer volt ampere converted into wattage. So 100 kVA transformer can provide 100 kilowatts of power, provided voltage and currents are sine and in phase with each other. So this is the ideal desire, and the deviations will come from these 3 points. Majority time from load side, many of the times for supply side, and some of the times some heavy load connected at the same point of common coupling. Okay. The time has gone where we had few generators giving all the electrical power. Now it is a distributed generations. So every household is having one small generator. So now many generators are supplying the power, and we really do not know from where the power what we are utilizing is coming. It may be from our adjacent our neighbor's house, and those inverter may not be a perfect inverter giving sinusoidal voltage. So power quality problem with this new distributed generation environment is a quite complex problem, and older theory will work out. So suppose protection system, we assume that generator voltage is fixed. Now this solar inverter, the voltage, if we try, we can short circuit the solar inverter, nothing will happen. So generation itself will stop, nothing will happen to generator. So these are weak sources, not like stiff sources what we had previously through gas turbine or hydro turbine. So that is how there is a huge scope. We need to revisit all our concept of protection, power quality, working with such utility supplies. So typical power system today may be represented like this. You may be having solar, wind, storage, okay, providing this electrical energy. Right hand side we have conventional grid. So conventional generation is also a major part. Solar and wind penetration is increasing, but this is also a major part. So different way people are utilizing this, like some remote area in northeast. So it is not possible to extend the utility grid. So all the sources may be integrated on the DC link. So all the sources, whatever energy they are providing, we can give to some common DC link, and load can also be DC. So such system we may say DC microgrid. Okay. You can convert these voltages generated by different sources utilizing inverter, and you can make it AC. And if you connect all load here, we may say it is a AC microgrid. So it is a microgrid in a sense, it is not having any connection with real grid. So, but still you have integrated many sources, small sources, maybe solar, wind. The beauty about solar and wind is they are of complement nature. So normally during daytime we have sun available, and wind velocity remains good during night time. So they are of complement nature, and they have intermittency, so they cannot provide constant power. So storage is always required. So we can store extra energy in batteries, and whenever less generation is happening through PV or wind, we can utilize storage, and the load requirement we can fulfill. Okay. The third possibility is hybrid grid. So you will have conventional generation also integrated with this. So over there, this grid synchronized inverter we required. So whatever AC this distributed generators are generating, that should be synchronized with the grid. Now there will not be any problem of meeting load power requirement, because variable power is given by this distributed generation, but now you have the utility grid available. Utility grid, you can assume infinite source of power. So the deficit power always you can draw from the utility grid. Okay. So in today's context, this is the typical power system what we can imagine. I have placed only 3-4 generators, but in I think will be many generators. Okay. And as I said, we really do not know from where my power is coming. Maybe from solar or wind or from conventional hydropower plant or somewhere. It is difficult to figure it out once they are integrated together. Okay. Now here I have a small question that where we should analyze power quality problem in this present day power system. Power quality will be of concern in which situation here? I expect some comment. No comments? So wrongly, many of the time we speak about power quality, like I am having variable frequency drive, and then we will say that my motor terminal power quality is not good. So we should talk about power quality only when utility grid is interface. So power quality will be of concern only with utility grid. For giving an example like brushless DC motor, it will give you more torque per ampere if you give quasi square wave current instead of sinusoidal current. So for such load, there is no meaning of analyzing such stator current and then talk about a TSD of that or power quality issues related with. So power quality will be of major concern where utilities interface and AC power control we want to control. Okay, so that is what I understand. If you have some other view, you may comment. So in theory, what all we analyze. So main thing is it is a network to supply electrical power. So how power transfer will happen, that should be clear. Incidentally, we have very few possibilities as a load. So we have only 3 element RLC and some switches in between through which we can connect and disconnect those elements. So we have a linear load, we have a non-linear load. Many times we are supplying such a load with non-sinusoidal supply. Maybe my inverter is square wave inverter, not giving sine voltage. So we are giving that. Okay. So we should be able to understand what type of power flow will happen between source and load, because that network is to provide electrical power to the load. Okay. So what is our normal method? So we know the supply system voltage. So from the impedance we will write current. Once the voltage and current are known, the product of voltage and current represent instantaneous power. So we will have third curve, that is power curve, that is multiplication of voltage and current together. Now that is not giving us any information. So its average value. So its value over a period of cycle. So we are having 50 hertz supply. So over a period of 50 hertz, what is the average value of that waveform, power waveform? So that average value is the net power what load is getting from the supply. So our network analysis we can recall. Then this term is very widely explored, power factor. Immediately student will also say cos of angle between voltage and current. But now scene is different. You are drawing non-sine current. So how angle between voltage and current? Your voltage itself is having non-sinusoidal component. So how to write power factor? Okay. So power factor is defined for maximum VA utilization. We can say unity power factor irrespective of shape of voltage and current. When volt ampere will be equal to wattage. So practical system, you will always find mismatch in wattage as compared to volt ampere. It will be always lesser. This value is real power factor, not cos of something or some other entities. Okay. So we need to revisit our calculation of power factor as well. Then this source side. So source side, previously we had a stiff source where nothing will happen to generator voltage. Now they are all weak source. So if you try to draw more current or if you do short circuit, the generated voltage itself will go down. In our network, at some point, there will be batteries also, storage also. So this effect of this weak source also we need to analyze. Okay. But what I commented, finally what we are looking forward is all loads should be resistive load. And then the possible. So utility would like to see all the load as resistive load. So whatever company is supplying power to us, they will have a maximum benefit provided full capacity of transformer they can convert into wattage and large number of consumer they can supply utilizing that power transformer capacity. So average power transfer, if you have some voltage, so this is a generalized expression, some DC voltage is also there and different frequency AC voltage is there. Current is also. So normally we multiply voltage and current and over a period of cycle we write. So we will have one term V0 I0 and then the remaining term where same frequency voltage and current transfers the power. So power factor new definition is it is a figure of merit. So how much power transfer will reduce? So wattage divided by volt ampere, that is the power factor now instead of some cos or sine terms. So average power or wattage divided by volt ampere, that is RMS voltage into RMS current. And that is the new definition of power factor. And unity power factor is one when Ohm's law is followed or everything will be felt like a utility. So modern day we have new type of rectifier drawing sine current. So they are power electronic circuit, but their end effect utility will feel like a resistance where the current will follow the voltage. So and voltage and current waveform have the same shape. So this is all power factor. Now briefly different case like majority time we have sine voltage and we are having linear load. Capacitor some combination. So RLC some combination. So it will just create phase displacement between voltage and current. So if you write power, power will come V1 I1 by 2 cos of angle between voltage and current. And V1 by root 2 is RMS voltage, I1 by root 2 is RMS current. So RMS voltage, RMS current into cos of angle between voltage and current. So here, what is volt ampere? Is V1 by root 2, I1 by root 2. So if we divide this average power by volt ampere, then power factor here is cos of angle between voltage and current. So power transfer is reducing only because of phase displacement created by load element RLC. Okay, so this is a linear load case. This is a linear load case. Another major possibility is grid voltage is sine, but we are connecting power electronics load. So power electronics load like half wave rectifier will draw DC current also. Full wave rectifier will draw non-sine current. So different frequency AC current via Fourier series, it can be represented. It can be represented. So this case, how to understand what is happening for power transfer? So method remains same. You multiply voltage and current and take its average value over a period of cycle. So intermediate steps I am not exploring. But this case also power value will come like this only. So V1 by root 2, I1 by root 2 cos of angle between voltage and current. Okay. Now here what volt ampere we are utilizing? So supply voltage RMS value. Now supply current is having many components. Though only fundamental current is helping towards power transfer. So non-sine current what you are drawing, okay, that is also unnecessarily loading your transmission line. So RMS current capacity of your cable is getting utilized by this current which is not helping towards any power transfer. So while you write RMS current, it is all frequency component square. So being a AC current, square root of that. So here we will have two factors now. So power transfer is reducing because of the phase angle between sine voltage and fundamental current, and it is also reducing because of this second factor. So numerator is fundamental current and denominator is RMS current. Okay. Many of the time we speak that in terms of TSD. So TSD is related with this term current distortion factor. Some can I continue or some feedback?
Yes, sir. Please continue.
So this is another practical possibility. Several power electronics load connected together. So power transfer is reducing because of non-sine nature of can correct that phase displacement. Then second factor. And finally, this distributed generation voltage itself is having harmonics now. So then it will be power transfer will reduce because of non-sine nature of current. It will reduce, and the phase displacement between fundamental voltage and fundamental current can also create this. Okay. Now on solution side. So older time, initially we had only resistive load, then we introduced motor, capacitor. So we require opposite element. So we require fixed capacitor to support inductor and inductor to support capacitor. Then later stage, a mechanically switched capacitor, inductor were introduced. This beautiful subject, SVC. So thyristor control capacitor, thyristor control reactor, FCTCR, fixed capacitor, thyristor control reactor. So thyristor series switch capacitor. So many arrangement based on thyristor were introduced. And effectively, the transmission line impedance we were modifying by connecting some reactor or capacitor. Okay. Even in today's scenario, if you practically see the in power quality APFC panels, it is all this SVC based arrangement. And to today's subject, VSC controller. So instead of thyristor, here we will use IGBT frequency, through which we will create a shunt arrangement, series arrangement, and a combination of that. Okay. Now, how do you compare last two? What will be the advantage of introducing IGBT in place of thyristor? So thyristor can decide. So once the current, nothing much running.
Hello. Hello.
Hello.
Sir, sorry to interrupt you, but your voice is breaking, sir.
Okay. Is it clear now?
Yes, sir.
So what was the point? Yes. So if we imagine some motor, heavy motor continuously running and some load at the shaft of the motor is continuously changing. So this thyristor based arrangement will not be able to rapidly change the reactive power what the motor is requiring working with different loads. So it will require several cycles to calculate what reactive power motor needs and then switch on some capacitor or reactor to support that. So and by that time the load at the shaft of the motor will may change, so some new reactive power. So the only advantage what we can have with IGBT based arrangement is, so this will work with a very high frequency. Operating as for supporting 100 kVR capacitor first. Then you will use thyristor to make that capacitor several branches, and then you will connect and disconnect. And that is how the reactive power required you can fulfill through capacitor. So for physically supporting 100 kVR reactive power, you require physically that component. So large number of capacitor, big size. Similarly, if there is a capacitive load, then big reactor you will require. Then afterwards, thyristor will come into picture to connect and disconnect that. Now, if you come down to SVC based fax controller, you are exchanging reactive energy at 10 kilohertz. So energy storage what you require is not at 50 hertz. So you don't require large capacitor, large reactor. So SVC based arrangement with a smaller inductor, smaller capacitor, we can do the same job what we can have with a inductor and capacitor with SVC. Here you don't require that large reactor and capacitor. So volume of this, so a real APFC of 100 kVA, one building space, one floor it will occupy where large there. Whereas the same 100 kVAR IGBT based, so it will be some small panel where one small chalk, three-phase chalk and one DC capacitor will be there apart from 6 semiconductor switches. So energy density will be very high. So in a smaller volume, you will be able to process a higher reactive power working with this IGBT based arrangement, and that is mainly because of the passive component requirement. So you require a lesser energy storage inductor and capacitor. So these are the different technology which we can utilize to mitigate these problems. So FEXT controllers are power electronics based system and some other static equipment that provide control one system parameters. We can have rearrangement, shunt, series and combination of these. So how to understand what all we can do in shunt compensation. So for example, this simple or basic power system diagram. So we have a sending end voltage V1, transmission line which is represented by some impedance R and X, and receiving end voltage V2. And here objectively we want to supply only active power. The type of load we will connect, it will draw reactive power also. If we say lagging current, some load we have connected. So V2 is a supply voltage there, and it is drawing some lagging current over there. So what will happen, or what will be the magnitude of V2? So V2 plus drop of transmission line is your sending end voltage. So this current I at an angle of phi. So your resistance drop we will add to V2, and then quadrature to that we will add reactance drop. So that is how sending end voltage will happen. This is the net effect. Sending end is sending this much voltage, but because of this lagging current what you are drawing, the receiving end voltage magnitude is less. So there is a drop of the voltage. There is a drop of the voltage because of drawing a lagging current through this transmission line. Now how we can overcome via shunt compensator? So at receiving end we will connect this VSC based shunt compensator. Now this source IQ will not be having any supply there. So it can exchange active, it cannot supply any active power. So wattage it cannot supply, whereas volt ampere reactive it can supply. So what is the physical meaning? So the current supplied by these will always make 90-degree angle to voltage V2. So that is a reactive energy. Now that current can be lagging or leading, but the phase angle between voltage and current will always be 90-degree. Okay. So what will be the advantage having IQ over here? So once again the same scene. We are having a lagging current. That current is decomposed into two parts. So current in phase with voltage V2 and quadrature to this. Now this quadrature current is locally supported at receiving end. We are not drawing it from transmission line. So from transmission line only IP voltage is coming. So resistor drop V2 plus resistor drop, and in quadrature reactor drop. So that will be my voltage. So now here if you check the magnitude of V2, the magnitude of V2 will increase because the reactive power requirement, and that not drawing from the transmission line. So as a result, drop R and X not happening because of the reactive current. It is only the active current in phase with voltage you are drawing from here. Okay. So this is how via providing shunt compensation at the receiving end, you can boost the magnitude of receiving end voltage. So V2 in this case will be higher than previous value. I hope it is okay. Some feedback. Participants or some questions. So this is the fundamental. If you can dive this much, then with power electronics, how to IQ, that will be the further explanation. This is what we are doing. Okay. Are you with me at least?
Yes, sir.
Okay. Who is speaking?
Sham, sir.
Syam. Okay. Syam. Thank you. So how to achieve this? So normally we will have what unit can provide this IQ current. So we'll be having 3 interfacing reactances, 6 and 1 DC link capacitor. So why the word VSC, that is voltage source converter. So DC link voltage VDC will always be constant. Okay. And what we are looking here is whatever be this V2 voltage, PCC voltage, we will be generating quadrature current here. So current through this inductor will be lagging or leading as compared to supply voltage. So that circuit can work without supply. So we don't have any supply here. We have only reactive elements, inductor and capacitor. Okay. So suppose you are having here RL load, and then this unit, this power electronic circuit should behave like a capacitor. So it should provide leading current. Then that lagging and leading current IQ component can cancel each other. If you have some capacitive load here, then this unit should draw lagging current. Then that reactive power requirement can be locally supported like this. So this hard line are the PCC voltage or resistance voltage, and this rise and fall is the current what this voltage source converter can provide. So first case current is leading the voltage. So the behavior equivalence is something like capacitor connected there, and second is 90-degree lagging. Both the cases there must be 90-degree. There must be 90-degree angle. Then only this arrangement can work. Now how I can generate lagging current and leading current? So inductor is a media. One end of this inductor is connected rigidly with supply system. Now another end through these IGBTs. So assuming that VDC is constant, so with fixed DC voltage, we can generate some AC voltage here. So magnitude of AC voltage, what we will generate at another end of this reactor can make this current lagging or leading. For example, first case Vs is there. So if the magnitude of inverter voltage, this V modulating is nothing but inverter voltage. So if the magnitude of inverter voltage is higher than your receiving end voltage, and both are having same phase angle, so inverter voltage plus reactor drop is your receiving end voltage. So when the magnitude of inverter voltage will be higher than receiving end voltage and same phase angle, then the current will be leading. Then the current supplied by this arrangement will be leading. Alternate case, here when the inverter voltage is lesser than that of your PCC voltage, receiving end voltage, then the lagging current this arrangement will supply. So both inverter receiving end voltage and inverter voltage should be in phase, and then only the magnitude will decide whether it will act as a capacitor or it will act as a reactor. So first case equivalence is capacitor, and second case it is reactor. Okay. So this is a beautiful arrangement where power electronics. So now I don't require 100 kVAr capacitor or 100 kVAr reactor. I am taking a small inductor, and at high frequency I am controlling these IGBTs and current through this inductor to follow the lagging current or leading current based on the magnitude of voltage I will be generating at the midpoint of this each leg. So this is some operation of shunt compensator, VSC-based shunt compensator. Any question at this instant? Somebody will say no question. Hello, participants. Some feedback? No feedback. So further, to do all these things in the laboratory, this is the model. So it works on 120 volts, so some step down 2 kVA transformer, then one power meter, which can reflect the sending end entities, anything, voltage values, current values, active, reactive power values, power factor values, everything multi-parameter meter can represent. There is a transmission line there, receiving end quantity, one more power meter. Then we have a 4-stage load bank. 4-stage load bank. So load power values we can measure through the third power meter. For shunt compensator, one MCB to connect the shunt compensator. For series compensator, another MCB to connect shunt series compensator, and one MCB to bypass the injecting transformer. So when we don't require series injection, you can bypass via one additional MCB. There are 6 IGBTs here and there will be 6 IGBTs here. So some microcontroller to generate 12 gate pulses there. What will be the feedback to the microcontroller is field information. So load voltage, load current. So that will go as a feedback. Being a voltage source converter, we will have to maintain DC link voltage to a constant value. So that another feedback will be given. Okay. And then some algorithm through which we will generate gate pulses for controlling either shunt compensator, series compensator or UPFC together. So you have already seen pictorially how, so 3 power meters, some 3-section pi network for transmission line, and then this shunt series compensator and load terminals. So this 3-section pi we created utilizing these values. So resistance 0.2 ohm, reactance 2.5 millihenry, and capacitor 10 microfarad each. So this is one pi section. This is one pi section, and there are 3 such pi sections. There are 3 such pi sections. Okay. Now for load bank, so number of rheostats, variable, bank 1, bank 2, bank 3, bank 4. Then those resistances can come in series with reactor. Then it is RL load bank. So we are varying RL load bank reactive power by changing current. So only R1 in series with L, R1 parallel R2 in series with L. So likewise, different reactive power this RL load bank can supply. Millihenry reactor was there. So around 0.6 power factor, whatever you have seen, that you can calculate. And capacitor was 200 microfarad. What other component we require is some microcontroller. So first day, whatever Junaid has demonstrated you, so same microcontroller kit we have utilized. Advantages are, I hope, now known to you. So it is very rich in form of a peripheral. So we require ADC to connect all these voltages, current, DC link voltage. So total 3 units of ADC, 12 AC are available. So we can connect them. A number of timers. So for calculating this gate pulses and other timing requirement. 17 numbers of timers this controller is having. Okay. Then DAC, so just like our MATLAB simulation where different instance, so you can connect scope and you can find out what is going on there, or we can debug where it is going wrong. So 2 numbers of DACs are also available, and these all things are available on chip. We are not to interface some other extra IC, only the microcontroller chip supports all these peripherals on chip. Okay, and it is quite fast, 168 megahertz, 210 MIPS. MIPS stands for million instruction per second. 1 million is 10 lakh. So 2100 lakhs instruction per second, or 21 crore in our language. Instruction it can execute in 1 second. Okay. It supports all DSP functions, So very rich. So that's why we selected this microcontroller. Programming part. So either through MATLAB you can do, or some C language programming where this software STM-Cube is available, through which you can create the project file. The second entity what you will need is a sensor card. So we need to sense voltage and current here. Voltage can be AC or DC. So this whole voltage sensor and whole current sensor card we have utilized in this development. So maybe 25 ampere current. Now microcontroller works with 3.3 volts. Its ADC reference is also 3.3 volts. So you cannot give some signal higher than 3.3 volt. So this sensor card will calibrate my full load current or full load voltage to that range. So maybe 300 volt is mapped to 3 volt. So whenever it represents 3 volt at microcontroller pin, it is actually 300 volt in the power circuit. So that is why we require this sensor card, where we can calibrate, we can reduce the magnitude of this sensor output to whatever we desired. So maybe 10 ampere is calibrated to 3 volt. So 3 volt whenever we are getting at ADC channel, it represents actual 10 ampere current in the circuit. And then linearly it will vary. So if you are getting 1.5 volt there, it will be 5 ampere likewise. Okay. So this is one major component what we require, because there are number of feedbacks: 3 load voltage, 3 load current, 3 inverter current, and 1 DC link voltage. So total minimum 10 numbers of input you require for this system to function. So this calibration will be there. So maximum voltage what it can measure. So DC link 500 volt it was calibrated. And then supply voltage, inverter current, load current, likewise. Then this shunt compensator. So design values are like this. So 10 millihenry reactor was connected, and DC link capacitor was 4700 microfarad, 450 volt. And the arrangement was operated with 300 volt DC link. Now this is the control logic part. So we will be sensing load current, load voltage, DC link voltage, and inverter current. So these are 3-phase AC. So total 9, and this is the 10th quantity. So inside what all calculation we are making. So from supply voltage, we will find out the grid angle. Utilizing this grid angle, so actual control is developed in DQ frame. So utilizing this grid angle, we can convert our supply voltage to DQ value. We can convert our load current to DQ value, we can convert our inverter current to DQ value. So actual control is developed in DQ frame. So we require all the values in DQ frame. So that is established by this two-step process. So first sense voltage, and from voltage you calculate the grid angle, and utilizing that angle you find out DQ value of load current, inverter current and supply voltage. Then we will have to maintain VDC to constant 300 volt. So VDC reference is 300 volt. Actual VDC we are sensing through ADC. So one PI controller will give me ID reference, how much ID reference we required. Now what about IQ reference? So if load is inductive, I need to supply capacitive. If load is capacitive, I need to supply inductive. So after performing DQ conversion of load current, whatever ILD will come, we will give IQ reference as minus of that value. So if it is inductive, from here it should be capacitive. If it is capacitive, from here it should be inductive. So IQ reference is minus of whatever be the load current Q value. So when you are changing load current, maybe from RL to RC or from 2 bank to 4 bank, automatically in closed loop, new reference for Q component will be given here. So this is how ID reference and IQ reference for inverter will be calculated. Then we have the standard DQ control. So actual ID and IQ value of inverter current, 2 PI controller, some cross coupling term will give me the inverter reference voltage VD star and VQ star. So what voltage we require from inverter to achieve this compensation. Now this VD DQ frame is our imaginary frame where we are making all this computation. Now actual inverter we cannot run in DQ frame. So as a result, now we will have to come down from DQ to ABC. So real what voltage you require at inverter terminal for achieving this functionality. So we require a reverse spark transformation. What is DQ to ABC transformation? So whenever you perform this DQ transformation, you require angle theta. So same angle theta what we have derived from supply voltage, we will be utilizing here. So after getting these three reference voltage, VA star, VB star and VC star, you can compare that. Suppose it is sine PWM, so you can compare this three sine wave with triangle wave and you can convert that into gate pulses. So this is how the IGBT gate pulses will be created. Okay. So please try to correlate the advantage of digital implementation. So we are giving this analog feedback. All these thing inside this rectangle is part of our program. So in software only we are writing all this. Okay. And the end outcome is directly the gate pulses. So controller will give us the gate pulses which can give us the desired performance. Okay. Now some test results. So for example, when this shunt compensator was tested with RL load. So only one bank is on. So small lagging current. So there you can see this is before compensation. So some lagging current it is drawing. And afterwards coming exactly in phase with voltage. Lagging current, inverter will provide leading current. So this green one is an inverter current which will be of leading nature. At full load, you will have maximum this phase displacement. So 0.6 power factor, what you have seen. Okay. So as you increase the load, you will be having large angle over here. Okay. After compensation, so once again current will come in phase with voltage, and this green one is this shunt compensator current. So for compensating lagging current, you require leading current. So this voltage source converter is providing this green leading current, and that is how at receiving end you have voltage and current in phase. Okay. Then a compensation of RC load. So when you connect one bank of capacitive load, you are getting leading current. So here the shunt compensator should draw lagging current. When you increase the value of current through that capacitor, so you will be having maximum possible leading. Okay. So this is without compensation load current. And when the shunt compensator will work, the current will be in phase with voltage. And how it will be achieved? So now the inverter will provide lagging current. So actual current is leading current. Inverter will provide lagging current. So that is how the total current will come in phase with supply voltage. So this is what is shunt compensation. Any question? Any comment? Any question? Hello, any question? Are you there with me? Participants? 23 participants I can see, but hello. Am I connected?
Yes, sir. Yes, sir.
Neeraj. So what I should do? I should continue or I should show some video clips where same performance they can observe because they are not speaking. I don't know how to interact with them. Syam, are you able to understand what I am speaking?
Sir, there are a few comments in a chat box.
Yes, sir.
Yes.
We could,
Syam is.
sir, we could able to hear, sir. Very nice, sir. Very nice. We are just observing.
You are observing. Okay. So I will play. I will take a question. I'll take question first, whatever are there, and then same performance we will try to see via that trainer, so that you can closely correlate whatever I am trying to speak. Okay. So beauty is now we can operate our IGBTs as reactor or as capacitor. As capacitor, and dynamically based on the load change, automatically it will be adjusted from capacitor to inductor. Okay. So can you speak those questions? At least if they are writing, I am happy.
Sir, there is no question from the participant in chat
There
box.
is.
They are just providing the feedback in chat box.
So they are able to understand. That is also sufficient for time being.
Okay. Yes.
So I'll play a clip for this shunt compensator, and then we'll take it further. Are you able to see the Google Chrome screen?
Yes, sir.
Okay. I'm playing it.
You can see the load right now. I have connected full quantity of load, and the type of load is RL load. So as you can see, the pink waveform over here, which is my receiving end current, and yellow is my voltage. So right now you can see my current is lagging with respect to my voltage. So we expect that as we will turn on my compensation, it will put this current in phase with the source voltage. So it will generate some compensating current uh, to compensate our RL load. So we will turn on our compensator using enter key. So as you can see, it is showing that system is on. So now you can see it will gradually increase the DC link voltage and it will gradually increase the compensating current. So you can see blue waveform over here is compensating current. So we have taken compensating current using DAC. Also voltage is coming from DAC, and the receiving end current we have terminated over here. So we are taking receiving end current from here. So right now you can see my statecom is taking leading current with respect to my voltage, and by that action we are getting the load, the receiving end current in phase with my voltage. And you can see the power factor of my receiving end is also improved. If you turn off the compensator using the enter key only, you can see gradually the DC link will be decreased and you will observe the decaying of our power factor. So as you can see, the power factor is 0.6. Now, when compensation was happening, power factor was around 0.9 leading. So now we will see how this is happening. So as I will turn on the compensator, my PI will take some Q reference. So my algorithm is, you can see the Q reference value over here. So my algorithm is setting some point of IQ reference, and using that only my compensator is taking leading current. Now if I will reduce the load, my leading current quantity will also reduce. So in accordance of that, my IQ reference will also reduce. If I will connect the capacitive load, then the polarity of my IQ reference will be reversed. So as I'm changing from RL to RC load, you can observe over here, my polarity is reverse minus 0.05. As I will increase the load in capacitive bank, my compensation will happen and IQ reference value will increase up to 4.3 at full load. As you can see over here, now the scenario is my compensation current is lagging because our load current is leading. So by that we are getting in phase receiving. You can see the load right now. I have connected
So I hope this gives you a feeling that over a wide range of capacitive to inductive high dynamically, this voltage source converter can provide a compensation, and irrespective of any loading situation, you will always get the reactive power is always supported by this compensator, not from transmission line we are drawing. Okay. So further, so this is what I demonstrated load performance, and with RRL load what happens. Now there is an opposite concept called series compensation. So same transmission line, same lagging loading. V2 is lesser than V1, huge drop happening that we want to overcome to one acceptable limit. So in series compensation, what is done is at receiving end, we will inject some voltage in series with transmission line. So load voltage is not V2 now, it is some V2 dash. So here current coming from transmission line, current flowing through this transformer, injecting transformer, and load current all are same. So here current is a reference, and this is also reactive energy supply instrument. So V compensator will be quadrature to the current. So the angle between IP and V compensator will be quadrature. Okay. So if we supply quadrature current, okay, then our V2, okay, what is V2? So it is V2 dash plus V compensator. So V2 dash plus V compensator is V2. And what is the sending end voltage? So in V2 we will add resistance drop plus J times reactance drop. So that is our sending end voltage. So here if you check the magnitude of V2 dash, what actually load is getting, so that magnitude has increased. So this magnitude is more as compared to V2, what it would have obtained in absence of this series injection. So this is how the via series injection we can also compensate the voltage quality problems. So if you check the power arrangement, majority are same. So there is a DC link capacitor, 6 IGBTs, 3 reactors. Now here it is the voltage that will be injected in series. So the role of this voltage source converter is to generate some voltage which we will inject via this injection transformer. Okay. So in terms of number of elements what we require to construct, it is the same. The difference is the voltage signal instead of current signal. Previous case we were producing lagging current, leading current. Here we will produce lagging, leading voltages. So some transformer is to 1, 500 VA, 3 transformers are connected. Okay. 4700 microfarad capacitor on DC link. Okay. And voltage source converter was operated with 300 volt. Some DQ based power theory I will not explain. Now this is the performance. So suppose RL load. So voltage now, irrespective of shunt or series compensation, at sending edge the effect is same. Our voltage and current are becoming in phase. So in absence of this series compensator, you will get that lagging angle, leading angle, but here you will come in phase with voltage. Okay. And for that what we are doing is we are injecting some voltage. So VC is injected voltage. So that injected voltage will make 90° with respect to current. So that is how it is only reactive energy what this unit is processing, and without any supply through capacitor and inductor we can design this unit. So only reactive power it can support. This is RC load testing. So in case of RC load testing, your current, blue one is a current which will be in phase, but injected voltage will make 90° angle. So with respect to voltage, this pink one is the voltage what we are injecting, and that is how VS and IS are coming in phase. Okay. So this is a dual of previous arrangement. Previous case through current everything was managed. Here through voltage signal everything was managed. Previous case receiving end voltage V2 was common. It is receiving end voltage also, it is inverter voltage also, it is load voltage also. Here current is common. So same current will come from V2 through injection transformer through load. Okay, so it is if you take in terms of network, it is a dual of previous arrangement. Okay, so three voltages are in series: V2, V compensation, and V2 dash, which is a load voltage now. Now finally we can have UPFC, that is combination of this shunt and series arrangement together. Okay. So we have seen in previous case that only quadrature voltage we can inject or only quadrature current we can inject. So in our transmission line, whatever drop is happening because of quadrature or reactive current, that is nullified. Now the current at receiving end are in phase with receiving end voltage. So if I still require further rise of voltage, if I require higher than that amplitude, so not only via reactive power, I require some active power also. Then this UPFC can do that job. So here what we have done is, so there is a shunt compensator. So we can draw some small amount of active power through this arrangement when both of them are working together, and we can inject through this series. So you can further increase the value of load voltage above what can be compensated through reactive power via injecting some active power. So you can draw some active current. So active current is in phase with voltage. So you can draw some in phase current also. So now the total current what we will be drawing here is active plus reactive. So no longer there will be a 90-degree angle between voltage and current here as well as between voltage and current here. Okay. But why we go for UPFC? So unified power flow controller. So irrespective of any situation, you can provide fixed voltage now. So maybe hypothetically make my voltage to same as sending end voltage. It is possible here. So we'll draw extra active power from here, and through this series injection we can increase the value of this voltage to higher than what can be possible with series compensation or shunt compensation. So these are the test result now. So at PCC, irrespective of any of these three arrangement, you will observe the same effect. VS and IS are in phase. Okay. So this is with resistive load testing. This is with RL load. So actual lagging current is changed to in phase current now. And here the magnitude of voltage, load voltage, you can maintain to some constant value. Now phase angle, you try to correlate the phase angle. So between injected voltage and the current, the phase angle is not 90-degree, but some angle which is lesser than 90-degree. So when we draw both active and reactive power together, that angle will not be 90-degree. Okay. So some angle lesser than 90-degree. So this is RL load testing with shunt series compensator. And when you take RC load, then also we can maintain load voltage to some constant value, and voltage and current and receiving end will always be in phase with voltage. So these are some result related with UPFC testing. The additional thing what you can obtain here is it is not only the reactive power drop we are overcoming, we can inject active voltage also, and as a result some constant voltage you can generate through these arrangements. Okay. So I think that is all. So finally, after many students projects, finally I have converted into this one trainer where all things are clubbed together. So different program you can load from here, and via this MCB arrangement, somebody may operate shunt compensator, that is statecom. Somebody may operate series, that is DVR, UPFC. So anything can be possible. Anything can be possible. So this is all about today's topic. So design and development of VSC-based fax controller. So in summary, I will say that VSC-based fax controllers can provide reactive power from some lagging maximum kVr to leading maximum kVr, and you require a very small volume for this circuit because these circuits are designed with high frequency. So as a result, you don't require large inductor, large capacitor, which is the case with SVC. So this is a technology where compact, small inverter sort of thing, maybe a 50 kVr unit or 100 kVr unit. So in a very small size, you can accommodate this. Whereas in actual APFC, you will have a big panel where physically you will have a large reactor, a large number of capacitors, which you are compensating. Okay. So I think with this I end here. So if you are interested in this practical based work, okay, you can follow these 2 pages of Facebook where continuously whatever such program we organize or whatever new development we are making, we are regularly updating. And second, at SVNIT, I have, as in introduction they said, I have designed all these courses where with practical based learning, how you can learn all these courses. So like first course of power electronics, those 4 conversion, instead of theory and those mathematics, what is the power circuit, and then we will write some program, get pulses, and then this conversion AC to DC, how it will happen. Then how to work with oscilloscope, multimeters. So that way I conduct all these courses. So those pages, any new course we organize, you will find the information. Recently we completed this course on drives, where all types of drives implementation we have demonstrated. Okay, renewable energy, another course we have designed where all this technicality, PLL, what is PLL, why it is required, MPPT, why it is required, PV inverter, PV statecom, then batteries, CCCV charging, all this can be demonstrated. The 4th course is on this SVC based controller. So people say IGBT, but real field information are with thyristor still. So higher capacity solutions still manufactured by industries utilizing thyristors only. So all technicality, how to generate gate pulses for capacitor switching, reactor switching, then series arrangement, FCTCR, one separate course. Okay. And then today's topic, this VSC based all development one can learn through all this small experiment. And then today I have not introduced harmonic, but if you take the problem of harmonic, then shunt, series filter, and unified power quality controller, that also can be taught. Okay. So normally we launch these as short courses, maybe of 1 week or 2 week. And the major thing or major good delivery can happen not via such remote talk. Physically, we all should be in the laboratory, and some small hardware with computer is given to you. And over there, some small concept of that subject we take, and then participants implement that and take their own call how easy the things are, and digest the concept of PLL and all that thing, vector control, all that things. Okay. So you may like these 2 pages. Then whenever next time such courses will be announced, you will get the information. One is this National Infotech page, and another is that Power Electronics Lab page. Students are regularly updating all the information over there. So I think with this I am done. So today's talk, I have tried to explain you the significance of power quality, then displacement power factor was the objective, a VSC-based fax controller, their technicality series with a little bit practical demonstration. I have tried to show you how they will work, and one laboratory prototype demonstration I have done. So thank you very much for your kind attention. And if you have any questions, you can ask.
Thank you so much, sir. I would like to request all the participants, if they have any questions, they can ask right now. Any questions? Sir, there is one question in a chat box. Where to see these courses?
I have spoken about that. So it is not like courses we keep organizing around these themes. So those laboratory pages are the source from where you will get, or you can drop me an email. I will include you in the email group. So whenever it will be organized, that information can be shared with them.
Also, there is one question in a chat box. How to mitigate voltage ride through capability inverters?
Can you elaborate? What do you
How
mean
to
by
mitigate voltage ride through capability inverters?
no? Question is not clear. How to capability
Mr.
inverter.
Mr. Sham, can you please ask your question directly to sir?
Sir, how to mitigate my voltage right through capability in inverters?
What do you mean by voltage right through capability in inverter?
Yes.
Wow. So it is related with some solar wind system or in standalone inverters. I could not correlate what is right through
Sir, in
capability.
standalone inverters, sir.
So why you require voltage right through capability? That is related to protection.
Yes, sir. Regarding protection only, sir. I have read in one of the papers regarding it, but I could not able to understand the concept.
No, but I think this is closely related with some renewable energy system where suppose fault is happening and then you will have to protect inverter against such currents. Then
Okay.
additional logic. So here statecom logic I have explained you in detail. So if you can
Yes.
incorporate additional protection unit logic over there, then you may say that my this solar inverter is having this whatever right through capability word, whatever you have utilized. So
Okay.
in a standalone inverter, normally what protection we provide, so it is designed for one capacity. So the user should not draw, or load should not draw higher current. So over current protection will be there. And then short circuit capability will also be there. So semiconductor switch, nothing should happen to semiconductor switch. Even a short circuit will happen. So such protections I have seen in normal conventional inverter, but this voltage right through I am not clear, but you can refer whatever literature you are saying. It must be related with some system, wind system or solar system, where additional protection feature you can incorporate. And
Okay.
how to do is programming part. So
Okay.
same feedback you are having, voltage, current, DC link voltage. You will have to find out that abnormal situation, and worst case what you can do is you can disconnect your inverter and you can protect the inverter against all such abnormality.
Sir, is there any type of material where I could able to get this details, sir? Materials are any related papers, sir?
You will find many articles. Means if you take wind generation, if you take wind generation, you will have many articles where only study will be related to this protection part, and not normal wind energy conversion system.
Okay. Thank you so much, sir.
Yeah, it's okay.
Thank you for your.
Any other question?
Sir, I have one basic question related
Right.
to the optimal placement of the VSC-based converter. So, what is the impact of the optimal location of the fact controller on the power quality?
You are putting me in a difficult situation. So normally power system engineers, so they do load flow analysis, and as a result, different buses based on the active reactive power flowing through the transmission line, you are having the effect on those bus voltages. So now your question is, FACS devices we can control, but what will be the optimum location where if we control, then those voltage profile will be as you desired.
Yes.
Okay. So Nilesh, only you need to study. What I can explain is how this FACS controller. So there are means in number of exam I have heard students where they present load flow analysis and then some neural network fuzzy logic or some way they decide that on this bus if we connect like that then this will happen and that will happen. But honestly, I don't have much reading around that and I clearly do not know how to decide. So some good power system engineers can help you or you yourself can try.
Okay, sir. Okay, sir. Thank you.
Optimum location apart. Okay.
Is there any question from participant side?
Sir, can you hear me?
Yes.
Yes, please proceed.
Yes, sir. Actually, I don't have a question, but I just want to answer some answer for Sham question. Actually, he asked me
Please.
right through system.
Voltage right through.
Yes, sir. When the time is low voltage, system will put consumption in the inverter side. If you see the data sheet of any inverter or any charge controller or any system, you can figure it out that information.
Okay, sir.
Okay.
Manikandan, sir. Yes, sir. I could able to hear, sir.
So this is the LVRT they are using. Suppose in case if they disconnect the voltage, for example, I will give you a small example, but it's near to that. Let's say that your system voltage is 210, okay, but actually 20 means that time there will be boost will be there. If your system is 20, it's still to work in the 180 also, it will boost to 210. Suppose if you are going below 180, sure the inverter will cut off. So this is what they are using LVDRT. If you are going for 240, it will come up with and it will work.
Right. So
Thank you, sir. Thank you so much. Manikandan, sir. Thank you.
Thank you, sir.
Okay.
So,
Yes, sir.
is there any final question? Okay, so we'll stop here, sir.
Thank you.
From the SSBT COET and from the organizing committee, I would like to say thanks to Dr. M.A. Mulla sir for sharing his valuable time and valuable knowledge with all of us. I would like to express my gratitude to Dr. M.A. Mulla sir and NITech because without their support, we would not be able to conduct all these three phases effectively. So thank you so much, sir, for your unconditional and continuous support to SSBT COET.
Thank you. Thank you. We are always there.
Okay, thank you, sir.
Thank you. So we'll stop.
Yes, sir.
Okay. Thank you all.